everything. And we use multiple sources of data to correlate and counter evasion techniques. For example, if a sample has a kernel monitor evasion, a kernel debugger evasion technique, and we would not be able to normally see it open a file or write to disk. But because we do multiple data sources, we also analyze the raw disk image, for example. So even if the kernel monitor, kernel debugger is evaded, we are able to see the activity anyway. Every area where we collect data, we collect it from multiple sources in a belt and suspenders approach. And because of this, it also increases our accuracy. And more importantly, all that data does you no good if you can't get to it. When you have this much data, you need to be able to get it. You need to be able to query and get the data. So these are very hard requirements to solve. $100,000 samples. We analyze at that particular rate, and we're doing more than that right now. One Windows virtual machine is created, started up, and terminated every second. Every second, there's a new VM being created, sessions, analyzed, done. We are post-processing the multiple data sources. Every sample we analyze generates about 1 gigabyte of raw data. Every second, we're generating 1 gigabyte of raw data to process and analyze. This is 1 petabyte of raw data in 24 hours. We convert the raw data into observation and traits. We distill it down, we analyze raw data into analytics for the database. Every session generates up to 30,000 index rows per session. Every day, we are generating 500 million rows per day in our database. So, what does it take to do that? 100,000 samples is 1 petabyte of raw data. 2 4 VNX racks, EMC racks. That's about $5 to $10 million just to store 1 petabyte of data. And we are generating that much data in 1 day. So what's the solution? Build a supercomputer. Build our own supercomputing cluster. We are building up our own in-house supercomputer. Our goal is to break into the top 500 list of the world's fastest supercomputers. We may be able to make it. Our goal is to be able to analyze 1 million samples a day in one single 42U rack. We scale up to 4,000 cores in a 42U rack. We draw 60 kilowatts of power. To give you an idea of scale and scope, the air comes out at 65 degrees Fahrenheit. So if you work with us, if you are a partner or as a customer, you have access to the resources. You have access to the data correlation with terabytes of data and trillions of rows. You have access to an API. And this is key significant. You have access to every artifact the sample generated. We store the disk image. We store the memory dump of the VM. We store all the artifacts that were changed on the disk. We store the network stream recording. All this is accessible to our customer or our partner. And we store this for every single sample we analyze. So let me get into the cool stuff about our technology and part of why we're able to scale. We wrote our own in-house kernel debugger, our own in-house Windows NT kernel debugger. It's programmable and scriptable. It's undetectable via debugger detection. We have a hypervisor level debugger. We hook in at the hypervisor level, so we are undetectable aside from the fact that we're running inside a virtual machine. Malware samples cannot say, hey, you're running a debugger, I won't run. Our kernel monitor captures all process activity. Files open, network connections, registry keys created, processes started, all that. And more importantly, our kernel monitor is fast enough that it runs in real time, 1 second of wall clock, 1 second of compute time. We have hundreds of thousands of debugger traps that happen during one session. Every time there's a debugger trap, we stop execution, we investigate the memory, we look at the functions that are called, we unroll the stack, then we log it, and then we go. And when we hit go, and if you do it hundreds of thousands of times in real time, you have to have a really high performance kernel monitor. I mentioned belt and suspenders approach. We do block level disk analysis. All file system changes are written to a separate file and a log. Every time a schedule block is written, it's logged to a file, a journal of what happens. Take from the low-level block level, map what changes happen at the NT file system level. Then we parse it, and we're able to tell you what files changed and at what time and how it changed. We detect changes. We also detect changes that do not map to NT file system because we are at a block level. We're able to detect rootkits that modify the raw disk itself. We extract and archive all file changes for further analysis. So if it drops, it reaches out to the network and drops a second malware or bootstrap, we are able to extract that and analyze it. And this is pretty cool. We actually analyze disk faster than check disk. We analyzed a disk comprehensively in under 10 seconds flat. So one of the things that I had emphasized in the past, if you're doing something, if your malware sandbox relies on modifying the guest operating system, you're doing it wrong. Because if you modify the guest operating system, it's detectable by malware. And I've seen many commercial sandboxes where malware explicitly looks for that commercial sandbox. And if the virtual machine crashes or the kernel crashes, well, you just lost your data. We do not use debuggers inside a virtual machine. We do not use special hook and DLLs. Our operating system image is plain vanilla Windows XP installed straight off a CD with Firefox, Flash, Adobe Acrobat, all the common attack surfaces of malware. And our kernel debugger in the future will support more than Windows. We have in-house an adaptation of our technology to do Android, Linux, and be it in Solaris. I've talked about the virtual machine and how we collect data. One of the most important parts is how we process. We preserve all artifacts generated by the session. We have a VM snapshot. We capture the CPU and process state. We have a memory dump. We dump out the entire memory so that we can go through it and look for interesting things. We capture all network traffic. We capture all file system, and we capture all process activity. And this is stored for every single sample we analyze so that we can go back and reanalyze our data as our technology improves. As I said, we permanently archive it. We use efficient delta and compression algorithms. So if 6 months later, you want to see a particular disk file that was dropped by a piece of malware, you can search for the checksum, and then you say, click on it, and it will extract it from that session that happened 6 months ago. Same thing for video, same thing for network traffic, and same thing for process memory dumps. Because we are behavioral based, we don't need to do a lot of code to support different file formats. Because if you have an Adobe Flash that goes across out to the network, it doesn't matter that it's Adobe Flash, because we see the behaviors. And that is one of the key abstraction technology we have. We only need to add support in terms of post-processing and static analysis. We are able to support all this, PE, PDF, JAWS, Flash, Microsoft Office, and we also support archive formats. If you want to put your malware into a zip file, we will be able to handle that. I hate XML. Every single piece of data we generate is accessible in an analysis JSON file. Every piece of data that we use to do analysis and correlation is also available to our customer or our partner or our user as a downloadable JSON file. It is moderately human readable. It is also machine readable. So you can read it, or you can write your own scripts to ingest the data yourself. What can we do with all this correlation? I'd like to show you it's all about one single sample and the amount of correlation we were able to do to find on that one single sample. Most sandboxes and antivirus companies, they pretty much just run it once and they're done because they don't have the capability to rerun the sample. And this is important. Malware is not static. I have seen malware change its behaviors day to day. Just because it behaves one way one day does not mean it's going to behave that way another time. A session is a snapshot at a given time. Many intelligence and antivirus evaluate whether the hash of a sample is good or bad. The same hash can be bad one day and good another. The same hash can be good on one day and bad on another. And this is a problem. If an antivirus vendor analyzes a malware sample with that same SHA-256 hash, and it decides that it's good, because all it does is it's just a game installer. It's obviously good. But a known good sample can change to an unknown bad sample. And many antivirus intelligence relies on whitelists. Congratulations, by adding the sample to your whitelist, you have just let malware into your organization because there's a difference between now and later. This particular sample is one of our favorite samples. We internally call it IRC test. We discovered it when we were looking for IRC traffic so that we could do protocol analysis. And I wanted to test my protocol IRC analysis code. So I found this sample. It uses IRC for command and control. And this is significant. 1 year ago, it was not detected by antivirus. It's a simple dropper. All it does is it reaches out onto the network, gets a URL, downloads the URL, and runs it. It uses IRC to grab the URLs and execute it. Very, very simple. About 60 kilobytes of code. We have run it almost daily for a year. It drops different artifacts every day. Use, forgot, forgot, we send about that, and every artifact behaves differently. This is one sample behaving differently on every single day that we run it. It uses public IRC networks for command and control, so it has a very long shelf life. With HTTP command and control, people take down the website and it's gone. But because IRC is on a public network, it's around for a long time. It's the gift that keeps giving. We have new artifacts, we have new traffic, we have new behaviors, and we have new evasion techniques to capture. One sample dropped all those different antivirus matches, the different antivirus variants, like Violet, Trojan Agent, Trojan Downloader, Trojan Agent, and that's just the top 15. I look in my database, we have about 60 or 70 different antivirus flags, and that's just the antivirus, what the antivirus companies know about. We compute a fuzzy hash for every single artifact we analyze. Fuzzy hashing means that you can compare one fuzzy hash to another fuzzy hash, and you can measure how similar the two hashes are. So if you have an antivirus variant, typically you'll see 70 to 90% similarity. We analyzed every single artifact dropped. We got 5 million relationships between artifacts dropped by the sample using SSD with 5 billion comparisons. It only took 4 hours on just one of our nodes. And the cool thing is, I mentioned that antivirus companies may not know about a sample, but by comparing the SSD hash, we can tell you that it's a new sample, a new virus variant that the antivirus companies have not found. I tried last night to get this data to display on my MacBook. Every time I did, it used up all 8 gigabytes of RAM on my MacBook. We have network traffic. Over 1 year, we saw it connect to 3,653 different IP addresses, more than 50 countries. Hong Kong, Romania, Russia, Ireland, South Korea, United States. I have actually a pretty cool visualization that I worked on last night to show distinct IP addresses it connected to and the country of origin. It's going to take a little bit to load. So I color-coded the nodes by what country it. Hello? There we go. That's an amazing amount of data for one sample. I mean, every dot is the IP address it connected to. On the outside, this is each session. So each session connected to like 8 or 10 different IP addresses, and we have all this. We have different colors for different countries, and you can see visually just how much data we got network-wise for one single sample by running it every day over a year. From our user interface, we're able to correlate to one session. We have domain, and then we have our IP addresses related to that single domain. So I'm going to show you a little bit of this. Let's pick a random one of this. So for every single session we run, we generate this report with indicators of compromise. For example, this particular one modified the executable file, stopped the Windows Security Center, outbound IRC communications, a downloaded file was flagged by antivirus, and modified auto-run registry key. It's a very bad piece of malware, obviously, because of all these indicators of compromise. But the cool thing is we were able to correlate on IP address from our reports. So I moused over the IP address, and I can see that it had outbound IRC communication and the DNS data traffic to this particular. Let's look at this. This is very interesting. I just click on the IP address that is connected to using HTTP. We can see all the domain lookups that were made against that IP address across all the sessions. So we collected domain data based on what domains are banned. We collected all the URLs that were made to that particular IP address. Then we collect all other sessions that also talk to that IP address in one way or another, whether it did a DNS lookup, whether it connected, whatever. So if you have an IP address and you search our database and our user interface, you're able to see all the correlation. And because our goal is to analyze the entire worldwide output of malware every day and put it in our database, we see everything. And because of that particular scale, if you should give us a SHA hash or IP address or a domain or certain behavioral traits, you will probably find correlations in our database and identify whether it's part of a crime family, whether the IP address is bad or not. And one of the most interesting things is we were able to correlate from one IP address 30 different malware variants. But if they connect to the same IP address, they're obviously related. You will never find this out by just looking at the binary, because they are completely different malware source code base. Like you can have Zeus, and you got Violet, and all that connected to the same IP address. And then we're able to make correlations based on that. We say, okay, this IP address belongs to this bad guy, this very specific bad guy in Romania. And if I wander here, I go to another sample. And I can just walk through the entire thing. DNS requests. TCP stream, we do protocol disassembly and stream reassembly on all our network traffic. Then we have, this guy made hundreds of network connections. Then we also dump out all the processes that will run. We're able to see what process ran what. So for example, we got this guy who changed 10 registry keys. And we're able to enumerate what registry keys are changed. And if you want to search for the registry key in our database, you can. So we're able to correlate based on registry keys, file paths, PE sections, entropy, everything. Everything is cross-correlated in our database. Let's see. And we have our artifacts that were extracted from a disk. And we do PE analysis on it all too. So we can see that it's encrypted, executable, and it's flagged by antivirus. And we're able to search for other, so often a dropper may be different, but what it drops may be the same, because malware authors use droppers to penetrate, to evade the first stage of protection. So we might have 100 different droppers dropping the same artifacts. So we run all that 100 artifacts, and then we see that it drops one single artifact. We're able to click on this and go back out and see every single other session that also dropped that. It's a very cool web. Let's see. One of the things that we do that is different and pretty cool are indicators of compromise. Each indicator of compromise is a logic system, like a SQL query, but it's more like logic as Prolog. And we have an expert system. We write expert system rules for each indicator of compromise. So then we are able to correlate on the indicators of compromise. So if you want to know what all samples that talk on IRC. All that high-level analytics based on low-level data. So not only are you able to analyze or correlate based on low-level data, you can do it on high-level data. So if you want to know where all malware samples that talk on IRC, you can search for that in our database. But based on this particular IRC communications, so you see all samples and all IP addresses and all artifacts dropped by that as well. Or if you want to know what malware turns off the Windows firewall, you can search on that in our database. So if you know a behavioral trait of what you're looking for, you know it turns off a firewall, you know it connects to a particular IP address, you could search for the intersection between the two and find other samples that are similar to the one you're looking at. So we mapped over this. Let's see. You mouse over, you'll see all related IOCs to that file. So if we click on that, or all related artifacts, and you will be able to download all the artifacts too. So if you find a file that you're interested in or a network stream and you want to look at it yourself, you can download it. So what do we learn from this one single sample? Honestly, I initially found it because I was looking for IRC protocol disassembly. That's easy. We also learned how to handle extreme static in these cases. One day, it decided to drop 20,000 PE files in our system. And I was not ready for that. So what happened was my sandbox code was analyzing every single one of these PE files, just bottlenecking a pipeline for a few hours. So I fixed that. I also increased PE analysis performance so that we were able to analyze a PE file in about 50 milliseconds. It was very important because we're analyzing up to 100 PE file, and the process dump is also a PE file. We also increased this analysis performance. Another day, it decided to saturate our pipe and download 10 gigabytes in 5 minutes. So that's another case where I had to optimize my network analysis code and improve the performance. And this is really cool. Handling some new evasion techniques that we saw. Basically, it dropped a PE file that mapped across the entire 32-bit address space of Windows. Most people run a 32-bit debugger. So guess what happens when you try to load a PE file into a 32-bit debugger? It consumes all available memory in that 32-bit operating system, crashes the debugger, and usually crashes your machine. Well, that crashed that particular instance. So I fixed that, and now I can handle this 32-bit executable 2 gigabyte memory mapping. So I'm going to show you the actual, if the internet actually cooperates. Does it always cooperate? Because that's why I have the virtual machine on my laptop. Let's see if I can connect to. we can upload a file. So let's see. Let's load Trojan exe. So we upload it, and it's off and going and analyzing the sample. So our goal is whenever sample we are submitted, we were able to get the data on that sample within 10 minutes. And more importantly, you're able to correlate that particular sample to other samples inside of 10 minutes. So that's almost real-time actionable intelligence. If you see a sample that goes into your organization and you're able to get data on it and what it does, who it is, and who it talks to, so if you know it's talking to a particular IP address, you can block it. Or you know it's dropping a particular SHA to visit some. You can search for it across your desktop to see if it's already contaminated. Now, this is one of the coolest features. You're able to interact with the virtual machine in an HTML5 browser. Well, hopefully this works with this bandwidth. Ooh. Any session you upload, you can get this. And you can interact with the virtual machine, you can interact with the malware. Our feature is called Glovebox. And so we're running our virtual machine inside the Glovebox interface, and this doesn't use Flash, it doesn't use Java, it works using HTTPS. It's all HTML5. And the latency and response is really quite good. I'm able to use this over a 3G connection. We basically wrote our own protocol for scraping the screen that's more efficient than VNC. We transmit PNG frames as they change. So we got Internet Explorer loaded up. There. And this is why we're having a kernel debugger in the background, capturing every single event that happens and log it. Most kernel debuggers that capture this much data slow down the virtual machine so much it's unusable. So we're obviously able to use the web browser. So let's click on View. And I have all those samples, and you have a view. You can mouse over and see all the IOCs related to that sample. So if you do a search for a particular sample, you can get this data, and within a few seconds do an eyeball whether or not it's interesting or not to look at. Most people are so focused on the whole idea of having a magic number. Is it good or is it bad? Magic numbers never work. But what we do is we present this information in such a way that somebody who is conversant in malware and Windows can say, hey, it's bad, in 2 or 3 seconds, rather than giving them a magic number that's maybe 1 second faster, and more importantly, it's inaccurate. So yeah, this very interesting sample here. So let's search for it here. and we have all the data that's in the sample. And we could, let's say I want to look for this particular URL. Anyway, I apparently have about 8 minutes left. So rather than keep on going, showing up my cool stuff, I'm gonna see if you have any questions you wanna ask me about malware analysis, automated analysis, or what I'm doing.
Hello. Hello. Thank you for a very good presentation. And I have a question about the packing capabilities. Do you do analysis, for example, after the packing, taking the ND5s of the memory?
Say that again, sure.
About the packing, after packing, also taking samples, what happened, and later be able to compare this to the data you already have.
Like, that's one of the problems with static analysis is you can't compare a packed sample very easily. So that's why our emphasis has been on behavioral detection. If you have 10 different samples that have the same, essentially the same code, but packed slightly different with a different key or different random number generator, you will see the same behaviors across these 10 samples, and you're able to correlate it. And here's the cool thing. We also dump out the memory. So by dumping out the memory, we have the unpacked sample as well. And we store that as an artifact. So if you want to download the unpacked sample, you can yourself. So you just run it through our sandbox, click on it, download it, and you got your unpacked executable, and you got your behavioral traits as well to correlate against it. Also, I've said that we do fuzzy hashing, SSD hashing on everything. But not only that, we also do fuzzy hashing on PE sections. So if we have the actual packed executable itself, the headers are going to be the same. So by doing fuzzy hashing based on the actual executable code that starts up and does the unpacking, we can do further correlation based on that. Yeah. Out there?
So, do you have any thoughts about how this could be used on the Android platform?
Yeah, easy. Our kernel manager is Windows operating system agnostic. All our kernel manager is a framework for hooking into a hypervisor. A debugger just puts breakpoints in a particular memory. It reads memory and it writes memory. And it reads the registers off the CPU. We have that code already. And we have written it in such fashion it's not Intel or Windows specific. So if you have an Android emulator that hooks into the hypervisor, or it doesn't need to be a hypervisor, I thought it would be very interesting to build a cluster of ARM computers to have hypervisors because that's more performant than actual emulation. We are able to analyze Android. We just need to take the time I just need to allocate myself or another engineer to take a month or two to do that. But then we're able to take the exact same techniques we use for Windows and put it in the exact same database. So if you have Android malware that connects to an IP address and you have Windows malware that connects to the same command and control network, you'll be able to correlate it based on that.
Any other questions for Wes?
Question here. Actually, what will be the role of malware analyst as a person, you know, after the system is doing all the things you shown us? I mean, we'll be out of jobs. Really, lame people can do it. I mean, you
No.
don't need a malware analyst to do.
I've said, we do not give magic numbers. I'm not intending to put you out of job. I mean,
No, I'm just asking.
yeah, but it's a very important point. We do this because we have to. We have to analyze 250,000 to 1 million samples a day. But what's more important is your role as a malware analyst needs to be looking at the actual intelligence. You become more of an intelligence analyst than trying to reverse engineer or dissect the malware. And that ultimately is more beneficial to whatever company you're working for than being the reverse engineer. We do all the hard work so you can do the more interesting things.
How do you deal with samples that require specific user input, say command line parameters or some sort of user interaction before they actually do anything?
Well, a couple of things. I show you the glove box. One of the cool things about glove box is it's exposed as a RESTful API. So you yourself could hook into Glovebox API and do some automation of analysis. If you want to say move the mouse or open the web browser, you can do that using the Glovebox API. So you can send keyboard commands, you can tell the mouse to move, and you can say wait for the next screen update or wait for the next Windows that updates.
Last and final question before we switch over to the next presentation.
All right. Thank you very much. I can be contacted at west@wetgrid.com, and you will see me around the conference if you wanted some more personal questions for me.
Thank you very much, Wes Brown.